Nekrasov first. So this conjecture can be seen as a purely combinatorial conjecture, and it is about solid partitions, which are informally four-dimensional piles of boxes in the corner of a four-dimensional room. Formally, what this means is we look at finite sets pi in the positive quadrant, set bigger than or equal to 0, 4. So finite sets with the following property. If you have a box A1, A2, A3, A4 in pi, and you have any B1, B2, B3, B4, with the Bi less than or equal to Ai, then it must also lie in the solid partition. That's the definition. So here you see there two-dimensional and three-dimensional analogs, which are known as Young diagrams and plane partitions. All right, so these are the combinatorial objects we study. And already in 1915, McMahon wrote down a guess for what the generating series of solid partitions are. So we sum over all solid partitions and then Q to the power the size. And the first guess one can make is it's the product from n is 1 to infinity of 1 over 1 minus Q to the n to the half n plus 1. And interestingly, the first 5 coefficients are correct, but then the 6th one is off by 1. So it predicts 141 instead of 140, which is quite interesting. Now, recently in physics, Nekrasov and Nekrasov-Piazzalunga discovered a measure on solid partitions via considerations of supersymmetric Yang-Mills theory on C4. And what I will do is I will introduce this measure, and then there will be a closed formula for the generating series if we enumerate solid partitions, but with respect to this measure. Okay, so let me introduce this measure. So to any solid partition, we assign a polynomial in variables T1, T2, T3, T4. Simply, we sum over all boxes, A1, A2, A3, A4, and then T1 to the A1, T2 to the A2, etc. So this is some polynomial. And furthermore, we assign a Laurent polynomial V of pi to the solid partition. Namely, it will be this Z of pi that we just introduced. And now there will be an extra variable y. So we take minus y times dual representation. So the dual is simply obtained by replacing each ti by its dual. And then there's a quadratic term, minus 1 minus t1 inverse, 1 minus t2 inverse, 1 minus t3 inverse, zz bar, zz star. So I think of this as a Laurent polynomial, which is an element of the equivariant K-theory of a point where we have two tori acting, a C star corresponding to this variable y. And now there's an important point. So we view T1, T2, T3, T4 as parameters of a three-dimensional torus, T, but we always will work modulo the following relation, T1, T2, T3, T4 equal 1. So later this will be a Calabi-Yau-4 condition when we realize this geometrically. So this is important. So now we have this Laurent polynomial, and we can apply to it a symmetrized K-theoretic Euler class bracket. So it takes, on monomials, it's defined as follows. If you have a monomial T1 to the A1, etc., y to the b, you simply assign to it T1 to the A1 divided by 2, etc., up to y to the b over 2, and then minus the same, but with negative powers. So this defines you a map to rational functions in the ti's to the half and y to the half, but again, modulo this relation T1, T2, T3, T4 equal to 1. So note here that in V pi, this is asymmetric in T1, T2, T3, T4, because the way it's written, you see T4 only appears in Z, but not in these coefficients. So this depends on the choice of direction. But now comes an interesting point. So how is this measure defined? So we pick a solid partition. We take the bracket of minus V pi, but we also multiply it by a sign. this is the most important part. So this sign is -1 to the mu of pi. And what is this mu of pi? So you count the number of boxes of the form ij in pi, where I is smaller than j. So again, this sign is also dependent on a choice of distinguished direction, namely direction 4, right? Because you see it's asymmetric in direction 4. But what's interesting is if you now combine this sign and this bracket of -v pi, you get some rational function. But this one is independent of the choice of distinguished direction, as long as you work modulo this relation T1, T2, T3, T4 equals 1. So this is the measure that Nekrasov assigns to a solid partition.
In what sense it is a measure?
Yeah, so maybe I just use this as an informal, that's a good question. Yeah, so in this talk, it will not be play any role. So you may as well just say a weight assigned to any solid partition.
But the weight is a rational function.
The weight is a rational function. Yes. So we need one further ingredient, namely, if I have a formal series F of a bunch of variables Z1 up to Zn, formal power series, I can take its plathistic exponential. It's the exponential of the sum from m is 1 to infinity of 1 over m, and then f evaluated in the variables raised to the power m. So this is the plathistic exponential. Okay, so then there's the following formula found by Nekrasov Piazzalunga, and this talk will be about its proof. So the formula states that now if we sum over all solid partitions and we sum this measure, then it's given by the following closed expression, plathistic exponential of bracket T1, T2, T1, T3, T2, T3, and then y, and then over T1, T2, T3, T4, y to the half q, y to the half q inverse. So again, if you look at this, it's asymmetric in the Ti's. But if you work modulo the relation, the Calabi-Alfort relation, this exponent is actually symmetric under permuting the Ti's. So this is the conjecture that I would like to talk about. So first, a few comments about this conjecture. One thing you can do with this parameter y, this free parameter, is you can specialize it to T4. If you do this, the measure will be 0 on all partitions that are not contained in the hyperplane x4 equals 0. So it will kill all of the solid partitions, and the only ones that remain are the plane partitions. And then this measure is the usual measure that you see in Donaldson-Thomas theory of Hilbert schemes of points on C3. And for that, there is a formula, namely the plathistic exponential of this very similar expression, where kappa now is the product of T1, T2, T3. So this was originally conjectured by Nekrasov and proved by Okounkov in his lecture notes on K-theoretic enumerative geometry, which will play an important role in this talk. Now you can specialize, so here it's a sum over plane partitions. Now you can specialize further. You can put the Calabi-L3 restriction, namely the product of T1, T2, T3 equals to 1. And then this becomes even more familiar. Then this just becomes McMahon's formula, the sum over all plane partitions of q to the power the size equals the product from n is 1 to infinity of 1 over 1 minus q to the n to the power n. Okay, so this will also later be used in the proof. I should also say that, yes.
I mean, it's kind of side question. And for Nekrasov, these two formulas and some other, it's what? It's a result of computation of some partition instant on partition function. Okay, so it's just a result of localization. Okay.
Yes, that's right, of a supersymmetric localization of some supersymmetric Yang-Mills theory on C4.
Mm-hmm. Yeah. Okay.
That's right. So I should also comment there is
So
a cohomological. Yes.
The question when k equals 1, so that means in the torus case that's
Right.
T4 equals 1. So
That's correct.
You have a one
Yes.
dimension getting smaller. Okay.
That's right. That's right. Yeah.
Thank you.
So also I should say there is a cohomological version of this formula, which was proved recently by Cao, Zhao, and Zhou. And they use a completely different method, a very beautiful application of degeneration in the Calabi-Yau fourfold setting, although they don't give the sign formula of Nekrasov Piazzalunga, and also they partially rely on the sign that we derive here. So what is the plan? Oh, and maybe I can mention there's also a higher rank version where you sum over tuples of solid partitions, which we prove as well. So what is the plan for this talk? The plan is to first give a definition of what these invariants are geometrically in terms of Hilbert schemes of points on C4. Then we will use torus localization to derive the left-hand side of the conjecture. And then we will use Nekrasov's factorizability machinery to derive the right-hand side. And then depending on time, I will talk a bit about origami, but as Jan already noted, maybe I may not reach this part. And in any case, Jan has heard that final section anyway. So let me just start with 1, 2, 3, and then see how far I get. So first, I want to study an abstract setup. Suppose we find ourselves in the following setting. We have some smooth connected variety A over the complex numbers, and on it we have a holomorphic vector bundle E with a section S. But let us assume we have some additional structure, namely a fiberwise symmetric non-degenerate pairing Q. So it's a quadratic vector bundle. And the section S is isotropic. So the quadratic form vanishes on the section. And throughout this talk, E will be of even rank. Now, in this case, you can build the following complex or morphism between complexes. You can take the differential of the section, which maps you from the tangent bundle of A restricted to M. So M will be the zero locus of this isotropic section. And also I will denote by I the ideal sheaf of this zero locus inside of the structure sheaf. So we have this differential ds, which maps from TA to E. But then after using the quadratic pairing, we can put the dual map here, the dual of the differential, which maps from E dual to omega of A. So that's because of the isotropy condition. This is a three-term complex of vector bundles, which I will call the virtual cotangent sheaf. And this will map to the cotangent complex of Illusie as follows. So the dual section will give a map to I modulo I squared, and then we can take the Kähler differential to go to omega of A. So in this way we get a map, and this will be, in the usual terminology, it will be a three-term obstruction theory. But as we can see from the formula, from the complex, it's self-dual. If we dualize this complex here on the top, we get the same complex because the outer two terms are dual and the middle term is self-dual. So this is a symmetric three-term obstruction theory. So let's call the dual of omega ver, we call it T ver. Okay, so let's recall just briefly. If you have a two-term obstruction theory, omega ver to the cotangent complex, then as usual you will have a virtual class in homology of real degree twice the virtual dimension, where the virtual dimension is the rank of this omega ver. And you also have a virtual structure sheaf in K0 of M, the Grothendieck group of coherent sheaf on M. And this happens very often when you study Gromov-Witten theory, Donaldson-Thomas theory of Calabi-Yau fourfolds, Calabi-Yau threefolds, on which we have several experts here in the audience. And also in Vafa-Witten theory, you find yourself in this setup. But today we are in the setup that we have a three-term complex, but it is symmetric. So in this case, it turns out there is also a virtual class and a virtual structure sheaf defined by O and Thomas. So in order to define it, we need an additional piece of data, namely a so-called orientation. So an orientation is simply a trivialization of the determinant of E restricted to N. And note, what we want is that if you square this trivialization, that you get the determinant of Q. So Q is the quadratic pairing. So the determinant of Q gives you a trivialization of the determinant of E squared. So an orientation by definition is simply a square root of this up to a sign. Now, one way of producing orientations, if you're in this ideal setup that we have here, is as follows. If you have a maximal isotropic subbundle of E, you get the sequence lambda mapping to E, mapping to lambda dual. And then this sequence gives you a trivialization of the determinant. So we will call this the orientation induced by lambda. Now, when you find yourself in this setup, there will be a virtual class, mver, and a virtual structure sheaf, OHAT mver. And there are some new features here. So first of all, they live in homology and K-theory with rational coefficients. Also this time, the complex virtual dimension is not the rank of omega ver, but half of the rank of omega ver. And finally, this virtual class depends on the choice of orientation. Okay, so what is this class? If you're in a setting where A is compact, let's denote by iota the embedding of M inside of A. And if you push forward this virtual class, it's nothing but the Euler class of lambda, if we use lambda to induce the orientation. And if we push forward O hat ver, there should be a hat here, then we get nothing but the symmetrized K-theoretic Euler class of lambda. So this is lambda hat of lambda dual, tensored by a factor, the determinant of TA to the minus half. So what is lambda of V? That's just the alternating sum of the wedges. And lambda hat of V is the same, but you tensor by a square root of the determinant of V inverse. So that's why we put Q coefficients here, so that we can take square roots of line bundles in K-theory. Later in this talk, it will actually be important that we can't just take square roots in K-theory, but later it will be important to actually take square roots of the line bundles themselves. So we need to show existence of certain square roots. Okay, so there is this general setup. So how are we going to apply this to our setting? So in our setting, we're interested in the Hilbert scheme of points on C4, which is a highly singular object. And we will realize it inside of a non-commutative Hilbert scheme. So one way of looking at the non-commutative Hilbert scheme, HilbCN of C4, is simply as representations of this quiver. So you just have one vertex with a dimension vector 1, with a dimension 1, and one vertex with dimension n. You have an arrow V, and then 4 loops, x1 up to x4. So these loops are endomorphisms of Cn, and V is a vector in Cn. And then there is a stability condition, namely if you act with polynomial expressions in the loops on this vector, you generate all of Cn. So inside of the space of all representations, this is an open condition. Now on this open subset, there is an obvious action of GLN, namely conjugating these loops and matrix multiplication on the left for V. And this is a free action. So you can take the quotient, and this is simply a smooth variety. So this non-commutative Hilbert scheme here is a smooth variety. And there's an easy way to cut out the Hilbert scheme inside of here. So if I take a point in the base represented by x1 up to x4, comma V, I want to look at a vector bundle, and let me just define it fiberwise. So fiberwise, this vector bundle is 6 copies of the endomorphism algebra of Cn. And why do I take this vector bundle? Well, as my section, I simply take the 6 commutators, xi, xj, between the loops. And then obviously the zero locus is just the locus of representations where the locus of elements where the xi and the xi's commute among each other. So this obviously cuts out the Hilbert scheme. Now, of course, what's on this slide is not specific at all to dimension 4. This you could do in any dimension. Also in dimension 3, but as is well known, for dimension 3, this is not the right thing to do.
Can you recall why?
Why? So one reason is that the virtual dimension will be negative. So whereas if you instead cut out the Hilbert scheme on C3 as the critical locus of superpotential, then you get virtual dimension 0.
Mm-hmm. Okay, good.
And interestingly, on C2, there are also 2 things you could do. You could C2, Hilb C2 is already smooth, so you could just take the smooth structure. But actually, you could also create a virtual structure on Hilb C2 by using precisely what's written here, and then you get that the Hilbert scheme of points on C2 doesn't have dimension 2n as for the smooth structure, but then it has virtual dimension n. And actually, those invariants were studied not long ago by Oprea, Pandaripande, and others. But anyway, that's so on C2 one can also look at this. But for C4, this is definitely the right thing to do because now there's extra structure.
Just a second.
Yes.
So in this construction of this M with the section S, so it looks like this is some sort of a Nakajima quiver variety doing this kind of a Hamiltonian reduction. Am I right?
Yeah, so maybe that becomes like at the very end in origami, that would be more the case. So in these Nakajima varieties, you also have usually these J's, and so I and J, and you would put those J's, you have some ADHM equation, bracket x1, x2 plus ij equals 0. And if you put the j equals 0, you would get this. So this is sort of sitting inside of those.
Okay.
But maybe we get back to that at the very end, actually.
Yeah.
But now what is special about 4? So, okay, so we have this. So the claim is there's in dimension 4 and only in dimension 4, there is also quadratic form on this E so that S is isotropic. So how is this quadratic form defined? So if we use fiber coordinates Vij on these 6 copies of NCN, then we can write down trace of V12, V34 minus V13, V24 plus V14, V23. And so this is a non-degenerate quadratic form. And if you plug in these commutators, you get 0. So this trick only works in dimension 4. And this should be viewed as the analog of having a superpotential in the 4-dimensional case. And we see more. We see also that we have an isotropic subbundle of E, which fiber-wise we can define as follows. So among our 6 copies of NCN, we take the direct sum of I smaller than j, but we set j equal to 4. So if you do this, you see that in this quadratic form, you see that the V12 is 0, the V13 is 0, and the V23 is 0. So this is indeed an isotropic subbundle. So this gives you an orientation. In fact, in our case, it's even better. E will split as lambda plus lambda dual. So this is the structure that we have for the Hilbert scheme of points on C4. Now, there is a problem because obviously our non-commutative Hilbert scheme is non-compact. So we would like to work equivariantly. So on the Hilbert scheme of points on C4 and the non-commutative Hilbert scheme, there's an action of this torus, this Calabi-Yau torus, simply by scaling the loops. X1 up to X4 go to T1 X1 up to T4 X4. And this action will also lift to the vector bundle E in such a way that the section is T equivariant. So why is there this Calabi-Yau condition? So this Calabi-Yau condition ensures that the symmetric pairing Q is T invariant. So it's similar to in the Calabi-Yau 3 story. If you work on the Calabi-Yau 3 torus, sorry, if you put the Calabi-Yau 3 condition, so that's a two-dimensional torus, the superpotential will be invariant. So likewise, if we impose this Calabi-Yau 4 condition, the quadratic pairing will be T invariant, and that ensures that the obstruction theory is T equivariant. And therefore, we will get a virtual class, Mn ver. So Mn here is shorthand for this Hilbert scheme of points on C4, Hilbert scheme of endpoints on C4, and An is our ambient space. So we get a virtual class of complex virtual dimension n, and it lives in equivariant homology with rational coefficients. And we get a virtual structure sheaf, O hat ver, and it lives in equivariant K-theory. Now, what's important here is to define invariance, it will be important that the fixed locus under this torus action is compact, and I'll describe it in a minute. And also for the virtual structure sheaf, you actually have to work in the localization of K-theory, which has to do with the fact that you have to invert some of the equivariant parameters. But I will not go into this. Now, as you can see, this theory is not of virtual dimension 0. The virtual dimension is n, so it is natural to put an insertion. So a natural insertion that you can put is the following one. On the Hilbert scheme of endpoints on C4, Mn, we have a tautological vector bundle O of n. And how is it defined? Well, over point Z, it's simply the global sections of the structure sheaf O of Z. So this is a rank n vector bundle. So what do? We take this symmetrized wedge hat, of the dual of this tautological bundle, and we put this parameter y, a formal parameter y. So this is the insertion that we put. And then the proposal is to look at the following K-theoretic invariants. So we define the following generating series, GQ. It's the sum from n is 0 to infinity of q to the n. And then on Hilp NC4, we take the holomorphic Euler characteristic of this virtual structure sheaf, O hat ver, but we tensor it with this K-theoretic insertion, this tautological insertion, which depends on a parameter y. And this is defined by localization. So this series will land in Q T1 to the half up to T4 to the half, y to the half, modulo the Calabi-Yau relation. So this is the generating series that we want to study. Maybe it's useful to remark that there's a cohomological version of this. Namely, you could also say on Hilp NC4, I look at the rank n bundle On, the tautological bundle, tensored by y, and I take just the Euler class. So this makes sense because you have a rank n bundle, so it makes sense to integrate its nth Chern class, its top Chern class against this virtual dimension n, complex virtual dimension n cycle. And what's interesting about this viewpoint is you can also study this in compact settings. So if you go to a compact Calabi-Yau fourfold, you can look at the Hilbert scheme of endpoints on it, and then you can also study this same generating series. And in the compact setting, together with Yalong Zhao, we had a conjecture for what the answer should be. And that formula was proved in many cases by Yeonjun Park using virtual pullback.
Is it always just a generating series in Q, or it's some kind of rational in Q?
Right. So let's see. Yeah, so for points, in the compact case, it will also be expressible remarkably as an infinite product, namely the 3D McMahon function, surprisingly. But if you start studying curves, Yeah, so it depends a lot on which particular theory you look at, because in this, so once you start studying Hilbert schemes of curves or surfaces, since the virtual dimension is not zero, there are many types of insertions that you can put. And for some insertions, you get rational functions after you divide out by the point part. But yeah, not for all. And it also then depends on whether you study Donaldson-Thomas or stable pair theories. So yeah, the short answer is it depends on the case. But it's also fair to say that, yeah, there's still a lot to study in this setup. So, but here they will they will not be rational functions. So here they will be infinite products when we do points.
Okay.
Yeah. Okay, so let's, so the first claim is that this geometrically defined series, G of Q, indeed is precisely what Nekrasov Piazzalunga study. So the sum over solid partitions of this measure times Q to the power pi. And the goal is to prove this using torus localization. Now, it's not surprising that solid partitions show up, because if we lift this T action to the Hilbert scheme of n points on C4, the first observation you can make is, so this T is the Calabi-Yau torus, it's three-dimensional. But it doesn't matter if you localize with respect to this Calabi-Yau torus, this three-dimensional Calabi-Yau torus, or with respect to the full four-dimensional torus, the fixed loci are the same. And well, for this, we know what the fixed locus is for the full torus, namely it's those ideals. So now we think of subschemes as ideals. Those ideals in the polynomial ring in 4 variables, which are monomial and which have co-length n. And those we can describe by solid partitions of size n. So how does this last equality work? Well, you take your ideal, you take the corresponding ring of functions, global sections of O modulo I. This is a representation with respect to C star 4, and you just record the weights of this representation. So this will give you some solid partition in the character letters. And this is an equality of schemes. So what I mean by this is a zero-dimensional reduced scheme. So the fixed points are all reduced. So it's certainly no surprise that we get a sum over solid partitions, but of course the interesting part is to find this measure. So for this, let us discuss the localization formula in the Calabi-Yau 4 setup. So let's say we're in this general setting again, where we have a ambient space A with a quadratic bundle EQ and an isotropic section S, and M is the zero locus of S. Now let us make some further assumptions. We have a torus acting on A and also acting on E, such that the section is equivariant. And we assume again that the quadratic pairing is T invariant, as we have in our setting also. And let us assume that the fixed locus of MT is zero-dimensional and reduced. So by the way, we do not need to assume that the fixed locus of A with respect to T is zero-dimensional. And in fact, this is not the case for the non-commutative Hilbert scheme. So we only need that MT is zero-dimensional and reduced. So then O and Thomas have a localization formula. If you integrate an equivariant class alpha over M ver, what is the localization formula? Well, you sum over all fixed points P and MT. You restrict alpha to P. And what do? You look at the Euler class of Tm ver at the point P. So remember, this is this three-term complex that is self-dual. So after you multiply it by a sign, it's a square. So it means you can take the square root. So compare this to the classical Atiyah-Bott localization formula in the smooth case. There you would just sum over all fixed points, alpha restricted to P, and then you divide by the Euler class of the tangent representation. So here you do the same, except for the virtual tangent representation. And because it's a square, you take a square root. But the delicate new feature in the four-dimensional case is the question, which square root are you supposed to take? And this is dictated by the orientation, as I will now explain. So let us suppose that E splits as lambda plus lambda dual. And let us pick the orientation O lambda. So it's certainly easy to write down A square root, namely up to a sign, the Euler class of TA, the tangent bundle of the ambient space, minus lambda at the fixed point. But the question is, what is this sign? So up to sign, and let me also record, there's a K-theoretic version of this localization formula, which is really what we use, where you sum over all fixed points, and then plus minus alpha at the fixed point, and then you divide by lambda hat of omega A at P minus lambda dual at P. But as I said, the interesting point is this sign. So this is what we will discuss. But before going to the sign, let's see what this measure is. So for any solid partition pi, let Z be the corresponding torus fixed closed subscheme. So what is this virtual tangent representation in this case? It's just TA minus lambda plus its dual. And actually you can also see in K-theory that this is the same as the derived form of IZ trace 3 shifted by 1, where IZ is the ideal sheaf of Z. So this we won't use, but this is sort of a sanity check that this is geometrically relevant. And now we take alpha to be this tautological insertion, lambda hat of O and dual tensor by Y. And then up to signs, you indeed get this measure bracket of minus V pi from the beginning of the talk. But of course, we haven't fixed the sign yet, and the whole point is to fix this sign. But at least up to signs, we see that we get Nekrasov's measure, so that's good. But now what about this sign? So the sign is determined as follows. Now let us go to a fixed point P, and let us look at the fiber of our quadratic bundle, EP, and let's take the fixed part. So in there we have our isotropic subbundle lambda, and we can take the fixed part. This is one maximal isotropic subbundle. But there is another maximal isotropic subbundle. So because the fixed locus is zero-dimensional and reduced, you can show that after taking the fixed part, this differential ds, which maps from the tangent bundle TA into E, is actually an injection. So this is a second maximal isotropic subbundle. And the sign is determined by comparing the orientations induced by these two isotropic subspaces. So if these two isotropic subspaces live in the same component of the isotropic Grassmannian, then the sign is plus. If not, then the sign is minus. So one way of expressing this is the sign is plus, if and only if the dimension of the intersection of these two isotropic subspaces is congruent half of the rank of the fixed part of F modulo 2. And another way of expressing it is as follows. Let PR lambda be the projection onto lambda. Then a formula for the sign is the following. You take minus 1 to the dimension of the co-kernel of the composition of the differential with projection onto lambda, and then you take the fixed part. So this is the formula for the sign. And the goal now is to calculate this sign in the case of the Hilbert scheme, where we have everything explicit. We have lambda explicit, we have S explicit, so we have everything explicit. So what is the calculation of the sign? So let me sketch it briefly here. You pick a point, a torus fixed point in your Hilbert scheme, x1 up to x4, comma, u. And let's say Z is the corresponding subscheme. So we're supposed to compose the differential ds with projection onto lambda and then take the fixed part. So from the explicit representation from the explicit way we described A in the section, you can see that this is nothing but the co-kernel of the following map. You go from 3 copies of the endomorphism algebra Cn to this the sum over I smaller than j of NCN. So these are also 3 copies of NCN, and then you take the fixed part, and the map is explicit. So you pick a bunch of matrices yi, and you map them to commutator xi, yj, plus yi xj. So this expression here is simply obtained by taking the differential of our section. And remember, our section is just the commutator. So that's why you get this explicit formula. And the goal is to calculate this co-kernel, which is still quite a bit of work. And it turns out, in the end, it boils down to calculating the fixed part of some X groups. Namely, if PR is the projection from C4 onto C3, projecting away from the fourth coordinate, it turns out that you have to calculate the dimension of the fixed part of some X groups on C3, namely the xi of projection OZ, and then the fixed part. And we only have to calculate these dimensions modulo 2. And if you do this, if you carry out this calculation, you indeed precisely obtain this Nekrasov-Piazzalunga sign formula. So that is this, this mu of pi here, this iiij in pi with I smaller than j. So indeed, this proves the left-hand side of the conjecture. So now let me talk about the right-hand side of the conjecture. So for this, we will use a completely different setup, a completely different set of tools, namely the factorizability notion of Okounkov. So the second theorem is that this generating series is the plathistic exponential of some series HQ. So HQ is a formal series in Q, and the coefficients are Laurent polynomials in the Ti's and y to the half. So that means, and then you divide by brackets T1, T2, T3, T4. So that means this H has no further poles in the equivariant parameters. So once you know this, you're already very far because you have at least found the structure of the generating series, and there are no further poles in H. So the goal is to prove this via Okunkov's factorizability. So let me recall how his factorizability notion works.
Mark, before you proceed, so the fact that your series can be expressed as a plathistic exponent, I mean, it's not completely unexpected unless you say that the coefficients are integer, yeah?
Exactly.
Because, yeah, okay.
And that there are no poles, exactly, because formally you could always write it like this simply by taking plathistic log.
Yeah.
And so that's right. And so the non-trivial part is that there are no poles in this H. Yeah,
Okay,
that's
yeah.
right. Yeah. And indeed, there are also integer coefficients. So how does this setup work? So we have so let's abstractly look at the setting where you have a smooth quasi-projective variety Y with a torus action. So this factorizability notion takes place entirely on symmetric products, not on Hilbert schemes. So let's define inside of sim m times sim n, let's define an open subset UMN, which consists of points xi, eta, so that their support is disjoint. And why is this a good thing to do? So let's look at the addition map from sim m times sim n to sim m plus n. So we simply add the points. So recall sim m just consists of unordered m tuples of points. And the good thing is if you restrict to this open subset UMN, the map, this addition map that we call sigma mn, is étal. So what is a factorizable sequence? So let's say we have a sequence of T equivariant coherent sheaves. So here there's a typo. I should say Fn is a T equivariant coherent sheaf on sim n of Y. So such a sequence is factorizable if you have the following. So for each m and n bigger than or equal to 1, on the one hand, we can look at Fm tensor Fn, right? Because on sim m we have Fm, in sim n we have Fn, so we can take that tensor product and restrict to UMN. And on the other hand, we have on sim m plus n, we have Fm plus n, and we can pull it back along our étal map. And for factorizability, we want there to be an isomorphism. And we want these isomorphisms to be natural in the following sense. So they should satisfy associativity. If you have M, N, and P positive, if you first add N and P, and then M and N plus P, you should get the same as if you first add M and N, and then M plus N, comma P, informally speaking. So this is the precise thing you want. And also you want a commutativity. If tau is the map that swaps the two factors, you want that phi of Mn is tau upper star of phi of Nm. So these are the two axioms. And then what Okounkov tells you is that if you have such a sequence, so each Fn here is a sheaf on sim m of y, sim n of y, then he tells you, and there will also be soon a work by Jürgen Rennemo in which he gives more detail and more explanation of this fact. If you have this setup, there will be K-theory classes Hn in the equivariant K-theory of Y for each n, so that you have the following formula. 1 plus the sum over all n of q to the n of chi on sim n of y of Fn has this plathistic shape. So it's the plathistic exp of the sum over all n of q to the n of chi on y of Hn. So this is what factorizability tells you. So our goal is to construct this factorizability data in our case. So how do we do this? So we want to use Y is C4 and our torus will be the Calabi-4 torus. Now, in order to construct, so roughly speaking, what we need to do is we need to lift these virtual structure sheaves to actual sheaves. So a priori, these autonomous virtual structure sheaves, they just live in K-theory. So you cannot apply this machinery of factorizability, because for factorizability, you need maps between these various objects. So we first need to lift the virtual structure sheaf to an actual sheaf. So for this, we need an intermezzo on spin modules. So abstractly, we are always in this setting where we have a smooth ambient space A and a quadratic bundle EQ of some even rank R. So when you are in this setting, you get a sheaf of Clifford algebras CEQ. So on each fiber, this is just the usual Clifford algebra, the total tensor algebra of the fiber, where you mod out by the ideal generated by the relations where V tensor V is equal to the quadratic form evaluated on V, V times 1. So this is also ZMod2 graded by keeping track of whether you have an even or odd number of tensor products. So let us define a left module for this Clifford algebra to be a spin if it satisfies the following property. So if it's locally free, and if S tensor S is isomorphic to the trivial sheaf on A. So here I put a dagger, by which I mean I look at the same left module for the Clifford algebra, but viewed as a right module for the opposite algebra. Okay, so spin means we look at modules over the Clifford algebra such that S tensor S is trivial. So here are a couple of facts. So firstly, about this quadratic bundle EQ. So étal locally, a quadratic bundle always has a maximal isotropic subbundle lambda. In our case, we will actually have this even globally. And once you have this, you can find a basis of sections, EI of lambda and FI of lambda dual, so that the quadratic form has a standard shape, namely Q of EI EJ is Q of FI Fj is 0, and Q of EI Fj is delta Ij. And now comes the important fact. So fiber-wise, the Clifford algebra is an Azumaya. It's a central simple algebra, so it will have only one non-trivial simple module. So what this implies is that étal locally, your spin module will always be of a very specific shape. It will be the left ideal inside of the Clifford algebra generated by the determinant of lambda. So inside of the Clifford algebra, you can look at the element E1 times ... times EM. So these are the basis vectors of lambda. So that's generating the determinant of lambda. And you look at the left ideal generated by this. So état locally, your spin module is always of this shape. And conversely, suppose globally you have a maximal isotropic subspace lambda, and you happen to have a square root of the determinant of lambda. But now I really want a square root as a line bundle. If you have this, you can form CEQ lambda, this module, globally, and you can twist it by determinant of lambda to the minus half, a choice of square root, as a line bundle. And then this, let's call it star, this module S is always a spin module. And then finally, it's worth noting, so far there are no orientations. So if you orient your bundle, the Clifford algebra has a volume form, an element that squares to 1. So locally, if lambda is positive, so induces your orientation, your volume form looks like the product over I of EI Fi minus 1. And why is this volume form interesting? So if you pick an orientation, you get this volume form, and the volume form will make every spin module into a Z mod 2 graded module, simply by decomposing into eigenspaces, plus minus 1 eigenspaces of omega. Okay, so these are some facts on Clifford algebra and spin modules. So finally, what you can do is if you have furthermore an isotropic section of your vector bundle, you can make your spin module into a complex, because in the Clifford algebra, your isotropic section will square to 0. So on the spin module, left multiplication by S will give you a differential. So what you end up with is that this spin module with S is a Z mod 2 graded complex. And what's interesting is you can then look at its cohomology sheaves. So if we view the cohomology sheaves as a Z mod 2 graded coherent sheaf, where we put the odd cohomology in degree 1 and the even cohomology in degree 0, then it's not hard to prove that this module, the cohomology of the spin module with respect to this isotropic section S, is actually supported on the 0 locus of the isotropic section. So it's supported on M. And finally, there's a technical result that somehow underpins our work. Suppose now you have this data twice. So let's say you have a smooth space A on which you have this data EQ orientation S and a spin module S. And on A0 you have the same, E0, Q0, orientation 0, S0 and S0. And suppose you have an unramified morphism between these two spaces. And let's say there are some compatibilities. So if you pull back the quadratic bundle, E0 is a subbundle. If you pull back the isotropic section, you get S0. Let us also assume that the determinant of the normal bundle of A0 inside of A is trivial, and the pK group has no torsion, the pK group of A0. And furthermore, there's a technical assumption on the way S should locally look near A0, which I will suppress. If you have all of this, you can show that if you pull back the cohomology of the spin module S viewed as a complex with respect to S, you get the cohomology of the spin module S0 with respect to S0. So there will be a canonical isomorphism like this. So how do we apply this in our setting? So we go back to the non-commutative Hilbert scheme, AN, and there we have our quadratic bundle, EQ, lambda and S, and our 0 locus, MN, which is the Hilbert scheme of endpoints on C4. Now, the first thing that's easy to show is, well, we have lambda explicitly, so you can just calculate its determinant, and you find that it's trivial up to an equivariant factor. So in our case, we indeed have a square root of that lambda as a line bundle. So then this general construction that I mentioned on this page gives you a spin module. So indeed, we get a spin module SS with S the differential. And now what you can show is that if you multiply the cohomology of the spin module with the total wedge of this tautological bundle, O(n) dual y, up to a factor of y to the minus n over 2, you get precisely this insertion O hat ver tensor lambda hat of O(n) dual y. So indeed, these cohomology sheaves that we created with this spin module, they lift the virtual structure sheaf times this Nekrasov insertion. So to prove this, you need a result of O and sweetheart. So let's call this sheaf E of n. It's, by the way, interesting to note that the virtual structure sheaf alone doesn't actually lift to a sheaf in the case of Hilbert schemes. So only after multiplying it with this Nekrasov insertion, which was symmetrized, so note that here there's a symmetrization and on the left there is not. There's some cancellation of square roots. So only this combination lifts to an actual sheaf. Okay, so now we can define a factorizable sequence. You take the Hilbert-Chow morphism, so you push forward the cohomology. Sorry, first push forward this En, total derived push forward to the symmetric product along Hilbert-Chow, and then you take again the cohomology sheaf. And this is the Fn, and these Fn's form a factorizable sequence in the sense of Okounkov. So then from this technical proposition, if you push forward from this technical proposition, you can actually create these isomorphisms between these sheaves. Fm tensor Fn on sim m times sim n, and Fm plus n on sim m plus n. And then you need to show that these phi mn satisfy associativity and commutativity. It turns out this only holds up to constants, but you can also show that this is still enough to run a factorizability argument. And then you get indeed that you have this specific shape of the generating series where HQ has coefficients that are Laurent polynomials in the Ti and y to the half. So maybe what is the end game here? So if I could maybe in a few minutes, I think I need only 2 more slides or 1 more slide. So what is the end game? So now you still have to determine this HQ. You have to show that it's bracket T1, T2, bracket T1, T3, bracket T2, T3 times bracket Y over bracket Y to the half Q, bracket Y to the half Q inverse. So this you should still show. So how does this endgame work? Now, from the explicit expression of V of pi, where pi is a solid partition, it's not hard to show that this term T1, T2, T1, T3, T2, T3 divides H of Q. So that's easy. And then the very final step is an application of Okounkov's rigidity principle. So also from the explicit expression of V pi, you can show that if you take the equivariant parameters Ti or Ti inverse and you send them to infinity, you can show that those limits exist. And you can use them to show that if you divide HQ by T1, T2, T1, T3, T2, T3, that you get something that doesn't depend on Ti's anymore, but only on Y. And if you know this, you can use the dimensional reduction that I discussed at the very beginning to determine this ratio. So actually, to determine H, once you have established this fact that H divided by this factor only depends on Y, the dimensional reduction fully determines the 4-dimensional answer. So that came as a bit of a surprise. You don't need to do new combinatorics at this stage. So that is indeed how the proof goes. Yeah, so I also had a further story on origami, but maybe, I don't know, maybe this is a good place to stop.
Yeah, thank you very much. Now, maybe I will ask you as my second question to talk a bit this origami story, because it's also related probably to this Zhongzhu question about Nakajima cover variety, that stuff.
Right.
But I have a question about this factorization. I mean, in 3D, yeah, okay. In 3D case, like in our paper with Maxim on this cohomological whole algebra, we introduce a notion of factorization system, which is maybe not exactly equivalent, so I cannot compare, but in many respects it's similar. And
Right.
okay, but yeah, you know that. But we used this factorization structure on cohomology of some equivariant cohomology of some moduli spaces, similar to what you do, because you take some sheaves, direct images of sheaves. We used it to prove that these Donaldson-Thomas invariants, motivic, they are sort of Laurent polynomial. I mean, they are well defined, like your HQ. So my question is there a kind of a general, kind of a more general framework or theory which kind of combine these two examples?
Yeah. I think this is an extremely interesting question, and this sort of similarities are so big that you indeed would expect that there is some sort of upgrade of your story to an analog of your story to the Calabi 4 setting. But to my knowledge, this is currently not there. So certainly, I'm not aware of like a common story that would combine this and what you have done with Maxime.
Yeah, and also, I mean, what we used it to prove more precisely that our generating functions, they are admissible in the sense that they indeed factorize as products or other quotients of products of these Packhammer symbols, like infinite, okay, with in some integer powers. And this admissibility property, it appears also, as far as I remember, in the work of Anton Melit. He reconsidered it pure in terms of symmetric functions and apply it, I believe, in the two-Calabi setting, but because he considered this computations of the number of points of the moduli of parabolic Higgs bundles and not parabolic, just a moduli of Higgs bundles. And basically, he needed exactly the same phenomenon, that certain rational functions do not have poles and they are Laurent polynomials with integer coefficients. And this admissibility played a really important role. So I believe that there is something, some machinery
Yes.
which probably people should.
Yes, and what's also interesting to note is that on the orientation side, like here we are in the lucky setting that the orientations are easy to create because we just find
odd
from the lambda.
Lagrangians and yeah.
But in general, if you're in genuine compact settings, the orientation question is quite a hard one. So if you're moduli of sheaves on a compact Calabi 4-fold, showing that orientations exist is a very difficult problem, I believe.
Yeah, that's true. Agree. Yeah, and maybe you'll tell more about origami stuff.
Okay. Yes, please. Please stop me if I would go too long, but I can say a few words about it.
At least few words. Yeah.
Yeah, so so the upshot is you have this quiver of Nekrasov. So yeah, let me just briefly go through it, just a few words. And it's some vast generalization of the ADHM moduli space. So you have for each A smaller than B between 1 and 4, you have a framing vertex WA, and you have an ingoing arrow and an outgoing arrow and 4 loops. And they satisfy a bunch of ADHM equations and some further equations. And then there's a stability condition and a GL action. So yeah, this looks very similar to this is sort of a 4D analog of a Nakajima quiver variety. So you could say these Nakajima quiver varieties are holomorphic symplectic. This object is up to a shift. It's shifted symplectic. So in what sense? So the claim is you can show, so again, let me not go over, there's some torus action again here as well, as you would expect. But the main observation is that, like in the case of the Hilbert scheme on C4, there is precisely the same description here, similar description. You can write down an ambient space, which is just the same quiver, but without relations. So you drop all the relations. That's a smooth space, obviously. And you can write down a vector bundle on it with a quadratic form and an isotropic section that cuts out this Nekrasov space. So what I claim is that these Nekrasov equations here, these ADHM equations, that they are an isotropic section of an appropriate bundle. And what then happens is, then you can more or less do the same things. Well, the part of the previous story on the Hilbert scheme, the first part, the localization part, you can do also in this case. And then you get an analog of that localization formula, except that this time the virtual structure sheaf turns out to be enough. We don't put an additional insertion. And what's also interesting in this case, there you can then get a certain measure that Nekrasov writes down in his BPS CFT papers. But what's interesting in this case is there's no sign, sort of a surprise. So you can do the sign analysis, use the sign formula that I mentioned before, but if you apply it, you'll find that the sign is always plus. And it turns out, even though in this case, the ambient space, the quadratic form, the section, they're all quite different from the Hilbert scheme case. But it turns out that for the sign analysis, at some point you take a fixed part, and it then turns out that the sign calculation collapses to the previous sign calculation of the Hilbert scheme case. Very strange, but it happens. So that's why you don't have to do a new sign calculation. And maybe what's worth mentioning to relate to Jan's work. So the very first thing you could do is you could look at this Nekrasov quiver, where you put all of the framings equal to 0 except for 1. Well, in that case, maybe unsurprisingly, you just get the answer of the ordinary instanton moduli space, namely a normalized chi-y genus of that moduli space. But then you can look at this case that Jan studied, where you put all framings except the ones involving 4 equal to 0. So you put 1, 4, 2, 4, and 3, 4 equal to 0. And now what's interesting is there are two descriptions of the same moduli space. So on the one hand, you can realize your moduli space as the isotropic 0 locus of a quadratic bundle. But on the other hand, as in the work of Rabchak, Soibelman, Yang, and Zhao, you can write a superpotential and cut out the moduli space as the critical locus of the superpotential. So in some sense, these are two virtual structures on the same moduli space. One is a -1 shifted derived structure, and the other one a -2 shifted derived structure. And then you can actually show that on the level of, let's say, K-theoretic invariance, you do get actually the same answer. But then what Jan does in this paper with Rabchak, Yang, and Zhao is you can restrict further to this Calabi-Yau 3 condition. So you also impose not only that T1, T2, T3, T4 is equal 1, but also that T1, T2, T3 is 1. Then the superpotential becomes T0 invariant. And then I believe what Jan shows in a very interesting paper is that you get an action of the coha, or perhaps a double of the coha, on the cohomology of this moduli space. And yeah, I think it would be very interesting if that story, if there's some sort of lift of that story to the full origami quiver. But here, yeah, we just make the observation that, like in the Hilbert scheme of points case, you can cut out the moduli space by an isotropic section, and you can calculate that the character that you get, including the sign analysis, is precisely what Nekrasov tells you that it should be. Okay, maybe this is good point.
It's very interesting. Yeah. So I know that people try to define this, what Nekrasov also expected, this four-dimensional generalization of Koha, but I don't think it's already kind of in any finite form.
Right.
Yeah. Okay. So questions now. Thank you very much. It's very interesting. Now questions from other people.
Yeah, definitely. My question is answered in this origami quiver. So this it's not exactly as an Nakajima quiver variety. Even there are additional conditions on this origami quiver. So the
right.
GA bar and the GA and the IA, there are some additional conditions here.
Right.
Mm-hmm.
And so it's also worth noting that these spaces are quite singular. So, for instance, an interesting case you could do is you could put two of the framings equal to 1, 1, 2, and 3, 4, and all the other ones equal to 0. And let's say you take instanton number 1. So this is sort of the first really four-dimensional case. And in this case, it's not so hard to just calculate what the moduli space is. And it turns out to be two copies of the affine plane, and the origins are joined by a projective line. So this is quite a singular object. Yes.
And for this origami quiver, so thinking of a representation, basically you are only attaching one single vector space V, because for the W1, do you have any control on the W1 tool? You can choose many different dimensions on the Ws.
Yes.
Oh, so yes. the Ws plays the role of the framing.
That's right. Yes. Yes. So in some sense, you have six ranks that you can all tweak. So it's a very rich. Maybe I should say I won't go into it, but maybe it's worth mentioning that what we also did is so in the case of Nakajima quiver varieties, there's a sheaf description due to BART, namely frame sheaves on P2, and we have a partial frame sheaves description here as well. So there is let me maybe not go into it, but there is a way of looking at a four-dimensional. So actually, in our particular case, you can go to P1 cross P1 cross P1 cross P1. That's a Fano fourfold. And you can look at the anti-canonical divisor and take half of it. That's some divisor at infinity. And you can look at framed sheaves that are framed at this divisor at infinity. So you can look at two-dimensional sheaves that hit this threefold at infinity. And the claim is that using this, there's an analog. You get an analog of the sheaves description of this of the traditional ADHM moduli space. So that site also seems to exist.
Yeah. So the Nakajima quiver variety, because it's not only about the quiver, but once you add up with the V's or the dimensions of a V, as you increase, you get the the characters for integrable representations. So I don't know, in this setting, this kind of complicated generating functions, can they be realized as characters of some D algebra or something?
Yeah, so I'm not really an expert on this, but I think Nekrasov has, in some of his papers, he writes things about Q characters. So I think there is a story, but I think Jan may be better able to answer your question. So
Okay,
yeah.
that's great. Thank you for telling me.
Yeah, for 3D in this paper with Rabchak, Yang, and Zhao, we interpreted it in terms of representations of Yangians, which kind of natural after the work of some other people. Yeah, but in general, 4D, who knows? But basically, the point is that there should be an action of some on the cohomology of these various moduli spaces of the tower of moduli. There is an action of sort of cohomological whole algebra or double it, and then for some particular moduli spaces you can see pieces of known maybe quantum groups. It depends. There is no even methods theorem which tells you what will you get. For example, in this 3D unequal force to equivalent branches, they found this representation of shifted Yangians, not exactly Yangians. So you can discover new type of quantum groups if you like. Yes, it's a difficult question.
Thank you, Ian.
Yeah.
And
Okay.
what's maybe also curious to mention is that the virtual dimension of this origami moduli space actually is generally negative. And so that looks like bad news, but it's still a non-trivial theory, because since you work equivariantly, in equivariant homology, you have negative cycles, so there's no contradiction there. You can still calculate. And then if you restrict to the case where the framings in direction 4 are all turned off, so the case that Jan explored, then the virtual dimension becomes 0. But if you put all the framings on, you get a negative virtual dimension. So it's quite a perverse thing, perhaps, to consider.
In the derived world, that's not quite perverse.
Yes, right. Yeah. And I think Nekrasov even noted this somewhere in the paper that.
In the derived world, that's very natural. Well, thank you very much for very interesting talk.
More questions? Well, if there are no more questions, so thank you very much. It's really excellent talk, very inspiring. Thank you.
Okay. Thank you very much for the invitation. It's great to give the talk.
Yeah, and so then this is it for today. Thanks